I'm audible in my series also is working.
Yes, yes.
So today is the week 12. My last week for PHF. Manav has one more extra week. This week 12 for NPTEL RL tutorials. So today we'll be studying about POM DPs. So you have seen the videos, right?
I've started it.
So you know what POM DP is?
Yeah, partially observed NGPs.
Plus MDP. Okay, so you know how a POM DP is mathematically defined, like what goes into.
No, I haven't gotten that far yet.
So you understood why POM DPs are used for modeling real life. Like real life MDP finding and MDP is very different. Like
Yeah,
what I believe is real life is very close to MDP, but the problem is you're not able to sense all the states of an MDP, so you go for partial MDP.
right.
There is an underlying MDP, but it is just our problem of not able to sense the state in which we are is what motivates us to go to partial observable MDPs. So you have seen the example that Prof has given, right? The box and robots.
Yeah, the boxes. Yeah.
Yes. Okay, so I'll just quickly go through that once. So maybe something like this. Maybe I should have and if your agent is here, then the states for the four, you have sensors which detect the four cardinal directions: north, south, north, east, south, west directions, whether you have an obstacle or not. And you could classify it with a four-dimensional state of, if it is not if there is no obstacle, then you do it with a 0. If there is an obstacle, then you do it with 1. So that whole thing is there. And then so first let me define what mathematically a POM is. So mathematically you have a state space, an action space, transition probability matrix, the return rewards that you get, and then this is known as the state of observations, and then an observation function. Okay, so could you tell me what are the state space here? So what is the state space?
The whole thing. The grid world.
Yeah, the grid world. So it basically gives you which box you're in. So if I number 1, 2, 6. So these are basically the box numbers.
Yeah.
Which box? Your action space?
Up, down, left, right, or northeast.
Yeah, up, down, left, right, or northeast. Okay, probability transition matrix. You have a probability transition matrix for the observation for the MDP. So POM DP is basically PO plus MDP.
Yeah.
So it basically is probability of conditional probability of state given x comma. So what is the probability? So since there is nothing stochastic in the transitions here for the underlying MDP, so it's just 1. So 1 or 0. So the probability is. So if you are at say state 8 and you take action north, then you go to state 6 with probability 1.
Yeah.
Okay. Yes. But now, could you tell me what this is? This is space of observations.
this will be the surrounding states, right? The
Yeah, yeah,
next.
yes, yes. So you will get activation of 000, 101, all those, like Sir has wrote those out,
Yeah.
00, 10, all those, the states of space of observations. Okay, so observation function, it is a function which takes states, actions, and the observation states and gives you a probability. So it tells you this, given your, so these actions, sometimes they are, sometimes they are not. Screen is stuck here.
You're lagging.
Yeah. Is my voice also lagging a lot?
Yeah, it was.
Now it's fine.
No, it's fine.
Okay. So, uh, so basically, what this function tells you is, given an observation, how probable I am that I am at some state. So you give an observation and you give a state. It tells you with what probability you might land in a state.
Okay.
Okay. So I think this also has Sir touched you when Sir told that. Okay. So yeah, maybe I didn't draw this properly. So this and this have the same observation, right?
Observation, yes.
So I think that's it. No other state.
And the right hand side, 5 and 7.
But 5 and 7.
5 and
Oh yeah, yeah.
9, 5 and 9.
9. Yeah, yeah. So these four are the same.
And then I think 2 and 11 also have the same.
As 4, 5, and 8, 9.
No,
Okay, these both have different. 2 and
2 and 11.
huh. So now, if you have an observation which tells you 0, 1, 0, 1, and I say state 4, so what the observation function gives you is 1 by 4, unless you have some prior belief. This is
Yeah.
what your belief is. So it's 1 by 4 if I don't have anything more prior to it. I don't know from where I came, how did I come there, and all. Then I just have. So suppose yeah, I came 2 steps from above to 0,
Yeah.
1, 0, 1. That means I can't be at 4. So then probability goes 0. If I know that I've come 2 steps from above.
Yeah.
But without knowing that history, just giving me an observation and asking what is the probability that I am at state, it depends on how you do this thing. So we'll do this belief propagation, or not propagation, maybe some simple stuff. So this is how you formulated your property. So you have states from the NPT, the action space from the NPT, the probability transition matrix. Okay, the reward, the expected reward, then observation states and your observation matrix. This is what is new. This is the belief state, or yeah. So it's not the belief state. Okay, so this is the observation function which tells you, given an observation, what is the probability with which I am at a state. So then there are history methods. Okay, so instead of doing all this, I'll just give a small problem on some property and try to show them how beliefs are calculated.
Okay.
You understand. So just a very small one. I think this is in your ungraded assignment for this one. So 2 questions. Small written. Just if you can't go. Okay, so the nomenclature is similar to the previous paper. So if you have an obstacle, 4 cardinal directions, obstacles. That. So now I want to find the probability of. So the question is, I throw my robot at the first step. At first step, I throw my robot in the grid.
Okay.
Uniformly random in these 5 states. Uniformly random in the grid.
Okay.
So the robot is thrown uniformly random Now you have gotten an observation. The observation is 0, 0, 0, 0. Okay, and your sensors are 0.9% accurate. 0.9 accuracy. They are 0.9, 90% accurate. 0.9 accuracy. So with 0.1 they give an error. And sensors are independent. Okay, and yeah. So now I want to calculate the probability of the robot truly being at state X given the observation 0, 0, 0, 0. How do you do this? Now you understand the question?
Yeah, so given that I'm at X.
No, it's not given that you're right. You
got an
observation.
Okay, I got an observation. So
the observation is 0, 0, 0, 0. What is the probability that I'm at X?
I'm not sure.
Okay, we can do it simultaneously.
Yeah.
Try to think like what would be the first step that you want to try to do. Like given a conditional probability, what first comes into mind? So I can calculate what. So conditional probability, I can write it as intersection
divided by the individual probability.
So this is the true state and this is the observation. This is the true state, this is the observation. This is just the observation. Okay.
Right.
So now, see, okay, what is the probability that I will be in X? The true state is X. What is the probability that I land in X?
1 by 5.
1 by 5. Let's see. Okay, and now I have landed at X. What is the probability that my observation matches? See here, observation and true state matches. What is the probability that my observation matches the true state?
0.9.
No, every sensor has 0.9 accuracy and each sensors are independent. There are 4 sensors.
Okay.
Okay. Each sensor.
Okay. So 4 times 0.9, but that doesn't make sense.
No, 0.9 power 4. Each sensor is independent.
Okay, right.
So first one into second one. Independence means you have to multiply and
yeah.
So 0.9 power 4.
0.9.
So this was the easy part. This is easy. Okay, so this is the difficult part. How do you calculate just the probability of observing 0, 0, 0? I'll give you some time to think because yeah, maybe 6 to 8. Like whatever you think of, just let me know. I'll tell you when you are speaking.
So number of states that have 0, 0, 0, 0 and divided by the total number of valid states.
Okay. So you are saying, okay, remember this is just the observation. So I am asking you, what is the probability that you observe 0, 0, 0, 0?
Yeah, so the number of states that have the same observation as the 4 zeros divided by the total number of valid states.
And the total number of valid states here are
5.
Okay, so as per you, this okay. I'll tell you maybe why it is wrong, because you need not observe 0, 0, 0, 0 only when you are at 0, 0, 0, 0. You can observe 0, 0, 0, 0 even when you are not at 0, 0, 0.
Right. The sensor accuracy comes into play here.
Yeah. Okay, so I'll tell you a small bit of this kind of things. So what you do is you try to find. So you have 5 states, right?
Yeah.
If it lands in one state, it can't land in any other states.
Yeah.
So you try to the observations, you try to partition it. So partitioning is like you make it into disjoint sets of the true things. So this is actually equal to probability of I land. Okay, let me call this by let me call this A, B, C. So probability of me landing at A and getting 0, 0, 0, 0 into probability of B. Okay, so yeah. So the total of probability is actually probability of getting 0, 0, 0, 0 given I have landed at A into probability of A plus probability of getting 0, 0, 0, 0 given I have landed at B into probability of B plus probability of 0, 0, 0, 0 given I have landed at C into probability of C plus probability of 0, 0, 0, 0 given plus probability of 0, 0, 0, given I have landed at X into probability of X. See, if it lands at A, it can't land at B.
Yeah.
So this term gets with what probability I get 0, 0, 0, 0, 0, I get 0, 0, 0 as an observation if it lands at A.
Right.
This tells you with what probability I get 0, 0, 0, 0 if it lands at B. This tells you with what probability I get 0, 0, 0 if it lands at C with probability. You have done all cases. There can't be another case. The robot has to land in one of those cases.
Yeah.
This is your this thing. Okay, so yeah, help me calculate the first term. So what could this be?
Yeah.
So
So
this basically boils down to 0, 0, 0, 0 intersection and so what is the probability that I land at A and my observation is 0, 0, 0,
0.1 power 2.
0.1 power
2.
2 and
And 0.9 power 2.
something else I think I said. What is the probability that it lands at
1 by 5.
1 by 5. So you see that I think everything would get the same value because 2 are wrong.
Yeah, right.
So it will be I think 4 into
0.1 square and 0.9 square. Divide by 5.
plus this x terms it will, this will have all come 21 which is all come.
Right. So that is 1 by 5 times 0.9 power 4.
So the probability that you land at x given 0, 0, 0 is 1 by 5 into 1 power 4 by 4 by 2. Okay, this is one of your graded assignments. So okay. Is this clear? Like we have solved it.
That's clear.
You understand that this is your belief of state X. This gets updated every day. So this is what you are like. So you have an observation. I want with what probability that observation gives me that I'm at state X. So
Okay, with what confidence I'll.
yeah, yes. Yeah. With what confidence you can say that this observation that I have seen belongs to state X.
Right.
That is basically this function. Give me an observation, give me a state, I'll give a probability which says you that you are so.
So if it's
Yeah.
1 by 5, right? if the sensor accuracy is 100%.
Oh, if the sensor accuracy is 100%. Yeah, absolutely. No. If the sensor accuracy it's 1.
No, sensor accuracy is 100%. Then the probability that I get observation 4 zeros is 1 by 5. I get it at only one place.
But this probability is 1.
Yeah.
Because if you get 0, 0, 0, and it is all these would go to zeros. This would just be 1 by 5 into 1, and here we would have 1 by 5 into 1. 1 by 5 cancels, you get 1. I hope this 1 is clear. Why it is 1 if sensor accuracy is 0.
No, not very much.
Okay, so you are given that your observation is 0, 0, 0, 0, and you know that your sensors don't make any mistake. So what is the probability that it will lie X? It will lie X because your sensor makes no errors.
Okay, makes sense.
And
Right.
it comes up here also. So now you are saying that your this thing makes no errors, right? So what will this happen is this will be 0 into 0. This will be 1 into 1. This term goes to 0, this term goes to 0, this term goes to 0, this term goes to 0. Only this term remains. Now this term would be 1 by 5 into 1 into 1 into 1 into 1. So the numerator is 1 by 5, as you have shown. And the error is, there is no error. So 1 into 1 into 1 into 1.
Right.
1 by 5, 1 by 5, you get 1.
Right. Okay, that makes sense.
Yeah. Okay, so I think this next question also is there in this the same question, but now I want a different problem. Okay, so this is a bit tricky, but okay, I'll same, everything remains same. The whole setup remains same, the accuracy remains same. Now I want to tell you that probability of I am at X. Okay. Okay, what is the probability? Not probability. I'm not at X. Okay. Observations 1, 0, 1, 0.
Okay. So we find probability using the same method for D, and then we do 1 minus that probability.
Yes. So yes, exactly. So you try to find probability of being at X given observation. So what is this? Like this is equal to 1 minus this, that is what it's like. Okay, so first we'll find this. So first we'll just find probability of X given observation 1, 0, 1, 0. So this is
P of X intersection 1, 0, 1, 0.
Right?
Given P of 1, 0, 1, 0.
So
we'll have to calculate P of 1, 0, 1, 0 now.
Yeah, maybe numerator would be easy first.
Okay, 1 by 5 times 0.9 power 4.
No. You are at X and your observation is 1, 0, 1, 0. But X's true observation is 0, 0, 0, 0.
No, I didn't get that point.
So you have observed 1, 0, 1, 0.
Yeah.
And you are at X.
Yes.
So that means your sensors has malfunctioned.
Okay, so it's with respect to the same diagram, as in we are dropped at the same place.
Yes, say everything remains same, just
okay.
The probability I am asking you to find the different probability.
Okay, so it's It's 0.1 square and
So
0.9
basically,
square.
think it of like you have found out the probability sensors are faulty and everything. So I'm giving you observation 0000. I'm asking you with what confidence you can say that you're at X. Now I'm giving you observation 1010. I'm asking you with what confidence you can say that you're at X. So
Okay, so I've made a mistake at 2 points. So it will be 0.9 square and 0.1 square.
yes. And then okay, so this one, yeah, maybe. Do you want me to keep the grid world in the so that it becomes easier? The denominator. So E 1010.
P of A intersection 1010.
Actually, this is easier. Like I do E intersection 1010. No need to do all the conditioning. It's just intersection. So when
Yeah.
1010 happened, it is a day. So to understand that partitioning and disjointing, so both can't happen together. That's what's happening. It's subbing them out.
Right.
If both would happen, then I can't sub them out.
Yeah.
Then probability would be some P of I need to minus the intersection between those two.
Yes. Yes.
The intersection here is 0, so I'm subbing them. Basically using the disjoint property of true states. So this will give you 1/5 into. Okay, what should A truly give you? 1, 1, 0, 1.
1.
And
So that's
1, 0, 1, 0.
it's 2 errors, 3 errors.
3 errors. So
0.9, 0.1 cube, and 0.9.
I think D also would give you the same thing.
Yeah.
What is D? 0, 1. D also give you the same thing, right?
Yes.
Yeah, so 2 into. These both are done. 2 into. Because same thing I'm just multiplying. So
Right.
What would B give?
D will give you 1110.
So
2 errors.
2 errors. So 2 errors.
No, wait, 1 error. It's only 1 error. It's my bad. It's 0.1 times 0.9 cube. And that's 2 times.
Pakka 1 error, I was thinking 2 errors.
No.
Okay, then I think C also would get the same. Right?
Yeah.
So 2 plus 1/5 into
Plus 1/5 into 0.1 square times 0.9 square.
Yeah. So I put this whole thing here. Then I get with what probability, if your observation is 0, 1, 1, 0 is 1, 0, with what probability I'm in state X. But then the question asked is probability of not at state X, I 1 minus that.
Yeah.
So you understand how beliefs are calculated, right?
Yes.
So there is this thing of belief propagation. So your P of S is your P of S. So now, what is your P of S is, uh, so given an observation, what state I am in, right? So now, your belief is just the probability of that state at that time instant. So now suppose at t you got observation 0, 0, 0, 0 with the same PODP set. This same POMDP set. Okay.
Yeah.
So now I ask you, okay, 0, 0, 0, 0, what is my belief for X? For what you say?
Probability of being in that state, which is 1 by 5.
No, which is this?
Right.
This is not 1 by 5. You need to calculate.
Yeah.
It's some big number, some number. I'm not sure what number you get, but some number between 0.0 and 1. It's not 1 by 5. It was 1 by 5. Okay, it's only 1 by 5 with no knowledge that it is 0, 0, 0, 0. With the knowledge that it is 0, 0, 0, 0, you can add something more. That's what I'm trying to show.
Okay. Makes sense.
So you're doing better than 1 by 5. 1 by 5 is, you don't even need the sensors to do 1 by 5. But now I'm telling you that I have sensors, I have data, that is faulty. Now what is the belief that you do? So that probability is this. So now every time you do this is known as, so now what happens is, initially you had 1 by 5 as your belief, right, with no sensors.
Yeah.
Now you have new beliefs. Now
Right.
this becomes your prior, and then you again update your beliefs post-belief.
Okay.
So your new B prime S prime would be summation over all states, transitioning from all states to that states which belief you are updating into your current belief. So this is how you update your belief. That will take a long calculation even for a small basic, but you can do it calculate. I hope you understand.
Yeah.
So what I'm basically doing is, your prior belief was without any sensors. Was 1 by 5, 1 by 5, 1 by 5. Now I'm giving you a faulty sensor. I'm telling you, okay, this is sensor observation. This is your probability of events. That problem. So now unless I do something else with the MDP, like MDP saying that, okay, I know that I have come from this state. I know that I have come from this state. So that is your probability of S prime giving me complex. If you do those also, then you can update your belief even further, saying that, okay, now I know that I am coming from this state. B.
Yeah. So we will maintain a history. View.
Yeah. You will maintain a history too. The history will be in the belief that you're updating. It's not in the transition matrix. The B prime of S prime, which will again become your PS. In the next
Okay.
This is how you update your beliefs. Sir gives you very okay. So form TPs, sir. History. You maintain the history, whole history. Maintaining the whole history is very difficult. So that is not proper. Then there are something known as U trees. This we fairly sure we also don't know. So,
Okay.
okay, then there is something known as QMDPs. Okay, so QMDPs, what you do is, so form MDP is partially observable plus MDP, right?
Yeah.
So you solve the MDP. But then, after solving the MDP, you have got the Q. So what you do is, first you solve the MDP. Just forget about observable, non-observable, everything. Just forget about it. Solve it. You know how to solve it. Right?
Yeah.
Use value iteration, policy iteration. Anything you use, solve it. Not only solve it. But while executing, you know that there is, I don't know which state I am in currently. So that I can find which queue. So what you do is, you do a score of action. Okay, this score of action I will do. Then you do summation over beliefs over all the QS. This is your, from your MDP that you are doing. And this is the belief that you are updating each and every day using this. Okay, so what this gives you is, and then what you do is you max, you pick max over score of. So what this is actually basically, now instead of state comma action, because you don't know what the state is, it is basically belief of the state comma action. That belief of the state goes here.
Okay.
That you are doing it over all states. So this S doesn't matter because it's something over all states.
Yeah.
Belief of all states. So suppose some state with the given observation has very high belief. So that state's Q function would be very high.
Yeah.
So with more probability you are giving that action with that Q value of that S comma A high priority, even if it has a low value, because that belief confidence is telling you that no, take that action which has, I think this is S prime and this is S prime, so that you sum over all S's. You get it. If this S, you understand the concept, right?
Yeah.
So basically what you do is you do Q belief of S comma A, and then you do the normal Q and B. What you do in Q learning. Instead of S, just use the belief of S.
Belief.
Then the thing is, belief should be updated using this.
Right.
Okay. Now the main thing is, this thing has okay, I'll not say no guarantees. It's very difficult to show that this will converge to the optimal policy of the actual entity.
Okay.
So maybe I'm framing it wrong. So actually what it says is, so you have an MDP. You have an underlying MDP. You know the optimal policy of that MDP. How you implement everything like that. Now when you are doing partially observable MDPs, depending on how observable you are, how your beliefs could be updated for which state you are in. Like there are very less proof which say that what conditions on P of S you need to have a tractable POMD, because you are not sure which state you are in. You can't guarantee that you will always reach to the optimal policy.
Right.
If you are sure at which state you are in, you know the action that has to be taken, you are done. But because there is an uncertainty of even which state you are in, you may end up taking an action which is telling you that is the correct action to take according to the MDP. But because you're not in that state, you end up doing something else.
Right.
But for many grid world problems and robotic applications, people have tested this and it works out fine. But there is no proofs for why it converges, why should it converge, as there are proofs for value iteration also.
Okay.
I think I'll flip it up. So these are some of the ways that probability session solve. So I'll just finish off actually by saying one thing. So all this whole tutorial we have heard about Markov models.
Yeah.
Okay, so Markov models, basically there are many classifications are there. I'm classifying into 4 types which we have used right now. So do you have control over your transitions? Yes. Do you know the state at which you are? Yes. Okay. Do you have control over transitions? First I'll go no. And do you know all the states? Yes. This is Markov chain.
Yeah.
Okay. This example, I think I've given one to you also.
Yeah.
State transition, just transition.
Yes.
If you're in state 1, it will go to other state, irrespective of what action. There are no actions.
Markov chains is basically MDPs with deterministic actions.
Exactly. Like, like, like very perfectly put. Yes. Yes. Okay. So actually very well put. So now you understand that if I have a Markov chain, I can model it as an MDP. If I have an MDP, I can model it as a Markov chain.
Yes, understood.
Because Markov chain, essentially the action that you're taking is what it's doing.
Yeah.
So if you have control over both, like if you have control over the transitions and you know the state in each other, that is
Plain MDP.
yeah, MDP. If you have control and if you don't know which state you're in, that is
POMDP.
And if you don't have control and you have these are known as hidden Markov models. I'm not sure if Harlan has touched on this, but this is basically your neural networks.
DQN.
DQN. The DQN have a neural network which learns your functions. So neural networks have hidden Markov chains. Those layers that you keep talking on about, like hidden layers and then layers to which that you do back propagation to gain a function. You know the function estimator, Q function estimator. Those things use HM. It's hidden Markov.
Okay.
Hidden Markov chains.
Okay.
So there you don't know what the state is, you don't even care what the state is, you just want to see where it goes to, stationary distribution of that.
Okay. Where does SMDP fit in here? I think it's both, right?
The SMDP is completely different. SMDP is not, it's a Markov product. SMDP is part of MDP.
Right.
Okay, and then the order of Markov process, right? So Markovity basically means
first order or second order.
So second order means you need two of the history, right? Third
order
means you need three. So, but whenever we say Markov model, we mean first order Markov models. So we are like, I want it immediately. And SMDP does not come under second order Markov. I hope that also is clear.
Yeah.
It is the transition takes time and a random amount of time.
Yeah, then there's a difference between nth order Markov model and SMDP.
SMDP, yes. I hope that is also clear. Okay, the last thing you see is probability bracket.
Yeah, it's vanished now.
So then there is CTMC. So this comes under Markov chains. So Markov chains has ETMC and CTMC. So reinforcement learning, everything deals with ETMC. Don't need to worry about CTMC. Like everything is discrete time. You want RL to be discrete time. You don't want RL to be continuous time. Continuous time is another headache that you get when you add continuous time to Markov chains. You don't want continuous time, but continuous times, Markov chain is basically, you can see a flavor of SMDP and CTMC. So I'll just tell you what CTMC is. CTMC is, you have a, suppose, continuous time Markov chain. Okay, one more thing is, Markov chain means that your state space is discrete.
Yeah. Yes.
Markov process means your state space could be continuous. So when it's continuous time Markov chain, it means that
states are discrete.
So I have discrete chains. So now suppose at time equal to 0, I'm at state S1. So in CTMC what happens is, it waits for a random time tau. This is tau 1 and then it jumps to some state S2. This state S2, this jump is depending on the underlying. So CTMC also has an underlying DTMC because there is a probability with which So DTMC is S prime given S, no action. So
Yeah.
given S, what is the probability? So basically on this probability, it will make a jump transition to some new state
Mm-hmm.
at tau 1. But this tau 1 is random. This tau 1 is basically exponentially distributed.
Okay. Okay. It depends like how SMDP depends on the option then.
Yeah, yeah. It depends on how SMDP depends on the option. It's exactly the same thing. But in SMDP, you had discrete times. They were discrete.
Yeah.
Here it's exponential distribution means it has a, so this time could be 0.5555 seconds, 0.22 seconds. Like here you run into all sort of problems because the transitions could be instantaneous. Like tau 1 could be 0.
Mm-hmm.
Instantaneous transitions would happen.
Okay. Okay.
So this whole CTMC is a very different thing and RM doesn't. But I'm just giving if you're interested in CTMC. Maybe now you would try, if I have a CTMC underlying problem, could you come up with an R lambda? Like interesting questions.
It was actually interesting, but how about we just replace time with steps, right?
Yeah, yeah. So
I take one step, then
yeah,
even I am discretizing it basically.
yeah, you're discretizing this. Yes. I think CTMC plus RL, I have not heard. I'm sure there are papers, but I've not heard. I hear in the other community people saying about CTMC with RL, like just discretize it because your reward functions everything. It makes sense. It makes sense to discretize it. It doesn't make sense to do different things. Could you come up with that? I think there are, but they are kernel-based methods or something. I'm not sure. Yeah. So I'm done for today. Like you have any doubts? 10 minutes and you have.
Right. Say let's consider a continuous state space, right? How would you go about discretizing? Yeah, continuous state space.
Oh, continuous state space discretizing. There's always a trade-off. How you go about discretizing it. So continuous state space. Grid world is an example, right? How you discretize it. So you have a grid world. So basically,
we used tiling to do it, right? In the course.
Yeah.
But how do you practically approach it? Like, what is a good way to discretize it? Say the tile length or something like that.
Oh,
right.
Like the tiling, those things now actually comes under. So given a problem, how big your continuous. So suppose the grid world is very big dimension. Like your robot has to search like some kilometer, like some 1 kilometer by 1 kilometer area. You don't do very small tiling. You take lots of data. Suppose you have just 1 room or 2 rooms or some say 5-6 rooms, some 50 meters by 50 meters. Then you can do small tiling.
Okay.
So it depends on what type of room. But you understood the tiling concept. Like how do I go from continuous to discrete? You can just make it into boxes and be done with it.
Yeah.
You can make the boxes as small as possible, but the more small you make, the more number of functions you have to do.
Right.
So what you do is the trade-off is go as small as you can go. Then once you have reached that, do that. Now you have all parallel processing. So what you do is in one processor you process few functions for that length of box. Just shift it. In the next processor, process the few functions of those. Shift it multiple times. How many processes you have, you shift it. Calculate this all, and you get that middle state. Like given a point, you will get multiple tiles. Just call those tiles from each and every processor one by one. So you see that it's not much computational power. The computational power is there, but you have the time because you have multiple processes. So that trade-off is there. How small you can go, and then how many processors you have, how much processing capacity you have to time it, how many times you can. Those are all like practical issues, hardware issues. But if you tile, so the math behind is that if you tile, you'll be the states. So instead of one box, the states in the box will be more closer to what actual thing is than just simply making it into a grid. So grid is better than tile. Tile is better than grid. Simple one grid will give you all the points. All the points here would have the same Q function.
Yeah.
But now if I tile it with shifted tile, then the states here would also have the Q function of this side and also have the Q function of this side and some average. So as you go closer, so what would happen is, so suppose you have a grid. So states here would have a Q value which is in between these two, and states here would have a Q value in between these two. So instead of Q value being one jump, so if I go from this grid to this grid, it will be multiple jumps.
Multiple smaller jumps, right?
Jumps,
okay.
Yeah.
Okay. The more fine grained you go, you will get a good estimate, better estimate of the Q value.
Better
But
estimate. The more
there's always a compromise with computational power.
Yes. So you see that as you go smaller and smaller, this would give you actually the actual theoretically speaking, if you do infinite amounts of time, you will just get the function, the Q function. The whole function. If you pick a point, you get the exact value of Q1 at a continuous function like this. So basically your Q function would be something like, depending on states, it will be something like this. And then if you increase it more, it will be something like this. It may go down also. But then as you increase it, it will converge to the original actual continuous Q function or the continuous. But this is very difficult to do because you don't have infinite goes to it.
Okay, so in RL setting, say if you encounter an unexpected situation which you have not faced before, how does the system respond to it?
Oh, that is a very good question, and that is, I think, another. I think we have not touched that in the topics, but what you are saying, unexpected situation, is basically dynamic MDP, right? Your MDP keeps on changing. Okay, so unexpected things. Okay, so I have two answers to this. Okay, I have 4 points. So I have 2 answers to this. Okay, so me being from a control bank, I see RL as an extension of control. So what I see is there is this nice theory on adaptive control. I don't know if you have heard of it. So adaptive control does not have underlying MDPs. It is not related to, it is related to RL in some sense, but it doesn't have an underlying MDP. But what it has is, there is an underlying model. So in control, what you do is you have an underlying model. That model is a set of differential equations.
Okay.
If you give a time, that model will give you at what place you are.
Okay.
So the solution to the differential equations is basically trajectories of your systems, how the states are going. Okay. So what the adaptive control says is, I don't know the model. I have some basic, similar to partial observer. I don't know the model exactly. I know that my model lies between this and this.
Okay.
And now I want you to give a control law such that I'll be safe. So where this comes up is, it is a very interesting topic. It comes up in, hello, I'm audible.
Yeah, you are.
So where this comes up is, suppose I have a rocket which is flying. As the rocket flies, it consumes fuel, the fuel decreases.
Yeah.
As the fuel decreases, the weight changes. As the weight changes, the thrust required to move some amount of instance or to do a maneuver changes. But how does the rocket know that its weight is changed? So here was actually, this question was actually what started adaptive control. So adaptive control is when you have this varying parameters in your system. You need don't know exactly. So I say, okay, you have gone some half percent, some 20% of your travel journey. What is your weight now? Compared to school? It will be different. You know it is between some range, but you don't know what that exactly is.
Yeah.
So you want to come to the conclusion. So this is what do you mean by unexpected circumstances? Like I have time varying, like my weight of the aircraft is changing at each and every point instant, and now I want to come up with optimal policy action. So policy is basically the control. So I want to come up with optimal policy so that I go from point A to point B. With heavy weight, turning I need different thrust. With lightweight, turning I need different thrust.
Yeah.
So those optimal thrusts changes as you go.
Yeah.
So there is this whole theory on adaptive control which does that. And RL, I'm not sure whether they have dynamic MDPs. I've not heard of dynamic MDPs where MDPs are changing. But I think they are. I think if maybe I'll stop the recording because we are just